So the solutions, if you on your RStudio session, you should have access to all of the RMD files that are behind the pretty website that we're using as our slides today. So if you click on number 4, the UMI section, and then scroll down to this exercise, so exercise 1 is here, then we have the solution. Nope, the solution is at the end. Here's the solution. So this is the solution to exercise 1. So for collisions, you just use the equation at the top, where n is 4 to the exponent 6, because that's the number of barcodes you have, for 4 different possible bases, to the exponent 6, which is the length of the barcode in this data set. And you just apply the equation. For sequencing errors, you first have to calculate the probability of an error using a binomial distribution with size 6, because that's the length of the barcode, and then the sequencing error, per base sequencing error. And then to correct for that, 1 minus the probability of an error is the probability of not having error, and then multiply that by the number of observed UMIs you have. And then we just round that up to get nice integers for downstream analysis. Any questions with that? Nope.
The whole UMIs have barcoding.
The barcode was 6 bases, and there's 4 possible bases. In theory, it should be completely random and equal chance for each of those 4 bases. In practice, this probably isn't the case, but no one has really figured out what the biases are at the moment. So for downstream analysis, I'm going to try and not stand in front of my own plots. So most of the current UMI platforms would have this feature where you have a very big spread of capture efficiencies across different cells. So here, each point is a cell. You can see we have 7-fold difference in the number of UMIs per cell that are detected, and a 6-fold difference in the number of genes detected per cell across this data set of about 800 cells, 300 cells. But I should point out this is just a feature of the 3 methods that are most commonly used for UMIs at the moment. In the future, hopefully this will change, and we'll have a nice sort of cluster of all the cells having roughly the same number of molecules and the same number of genes detected. But this is the current state of the field. Oh, the solution? Sure. So the equation here for saturation, n, this little n, is the observed number of UMIs. So that's the matrix we've given you of the observed number of UMIs. Big N is the total number of possible UMIs. So that's 4 base pairs to the exponent of the number of bases in your barcode. So this is 6 bases in the barcode, so that's 4 to the exponent 6 to get the total number of possible barcodes. And then you just use this equation for 1 minus that logged times minus that was approximately, will approximate what you should see if there were no collisions. Oh, and the solution for the binomial distribution? So you use the binomial distribution because you have 6 bases. In each base, there's a probability of 0.1 of having a sequencing error. So the probability of having a sequencing error in any of those bases is 1 minus the probability of not having an error in any of those bases. So here we've got the probability of having 0. So that's 0 errors. When there's a probability of having an error of 0.01, per base, and we have 6 bases. So this whole thing here is the probability of not having an error in any of those 6 bases. So 1 minus that is the probability of having an error in any one of those bases. So we just do, again, the probability of having, do 1 minus that to get the probability of having an error in any of those bases, times the number of molecules to get the errors, right, for the errors. Yeah. Right, so I've been talking about this problem. So recent analyses, most people, you end up pooling cells and genes together based on cell type or for genes biological pathway to increase your power to detect things, because you have this problem with detection rate. But robust statistics for dealing with this large spread of detection rates is still an open question. So there's no good methods for dealing with that at the moment. So we have exercise 2, where now you can load the reads as well, and then plot the variability of capture efficiency for this data set, and then try and estimate the amplification rate, so the number of reads per UMI. So how many times are we seeing each of the UMIs in this data set? Oh, so capture efficiency is this plot. So number of molecules versus number of genes detected.